differentiation, and it does. Yeah, so people just say I call automatic differentiation and it does the thing I want it to, right? That's this feeling across scientific machine learning. And what I want to do today is I want to scare you a little bit. Like this is going to be the spookiest math talk you might have heard in a while, right? And the purpose of this is to bring back numerical analysis, right? So, what is numerical analysis? It's the study of whether whether the mathematical implementation or whether the implementation of our mathematical objects actually gives us the numbers that we expect them to be when when we're factoring in all of the details about how computers actually work, right? And what I want to show you today is that there's actually a lot of issues with automatic differentiation getting to the correct answer, especially when you're in the context of physics, and what you need to be thinking about, what you need to be considering, and how this means that you need to think a little bit more than just getting the math correct. There's also a numerical aspect that has to be correct, right? So let me go into this and you'll see exactly what I mean. So first of all, just kind of set up the what is the setup here? What are we actually trying to do at the end of the day? We're trying to do scientific machine learning. And scientific machine learning in a nutshell is this idea of we have scientific models and we want to be able to mix them with data, right? And in fact, the way they like to say it these days is that, scientific models are actually an encapsulation of heterogeneous data. If you think about, for example, general relativity, right? If I was to ask you what is like the 8 billion row data set that describes how general relativity, the equations of general relativity, you wouldn't be able to point to a Google-sized data set to train an AI on. And the reason for that is actually pretty specific. And it's because the reason why we believe general relativity is true is because of a multitude of different data sets, right? So, for example, we know from the perihedron of Mercury, right? We know that gravitational lensing around the moon, get gravitational lensing around galaxies, the existence of black holes, right? All of these are different pieces of data that tell us that the equations of general relativity are correct, right? And so there's no data set to do machine learning off of if you wanted to train an AI to make it recapitulate, machine learning, right? The equations themselves is our best encapsulation of a multitude of different experiments and many different heterogeneous data sets, right? And so in some sense, we want to be able to use our scientific models and on the same footing as data because they are effectively a very large or infinite data source of things that we know to be correct, right? And the goal is to be able to construct predictors such that when we pour in, more models, we can use less data to be able to get to the same amount of good predictions that, Google would use of, the entire corpus of the internet to be able to do training on, right? So one of the key methods that we use inside of this is these universal approximator differential equations, where the key aspect that we're doing here is we take the idea from machine learning that neural networks and other types of objects that are related are their core property is that they're actually just universal approximators, right? They're functions that take in n inputs and m outputs, where if you just make the neural network sufficiently large, it can approximate any possible function, right? You can formalize that in the universal approximation theorem, which is just that, for any Rn to Rm function over a compact space, there exists a number of hidden layers or depth of the neural network such that for all nice functions f, there is a choice of the parameters for the neural network such that the input, the input to output behavior of this neural network is epsilon close to that function you're trying to approximate over the whole domain, right? So there's a mathematical formulation of this, but basically the idea then is that a neural network can be any possible function. You just need to find the right weights for this, right? And so the way that we begin to use this is we say, what if we're building mathematical models, but we don't necessarily know all of we don't necessarily know all of the functions, right? So here, for example, I'm writing down a partial Loc-Volterra equation where I'm saying, okay, if you leave bunnies in a room, you'll get exponentially more bunnies. If you leave wolves in a room, they'll all eat each other, and so you get exponentially less wolves. But if you put bunnies and wolves in a room together, there's some end to this story that's never been told to me, right? And so what happens when rabbits and wolves go into the room? I don't know. There's some function I don't know inside of this model, right? So basically the neural network's a way to be able to represent I don't know what the function is, right? And be able to turn that into a continuous learning problem of parameters. And that second part is the part that we'll mention a little bit before we get onto the next section, right? But then what this actually then looks like is you basically can write down everything that you know about a scientific law, and you can use this to be able to be discovering what the other parts of the law are, right? So here, for example, is a nice example of doing this from 2021, where back then they said, okay, what LIGO actually found with the black hole. So the first detection of gravitational waves was done on a binary black hole system, right? And so what they did is they said, okay, let's actually take this data and we say, we have two black holes that are moving around each other in a rotating frame, right? So this is Newtonian physics in a rotating frame. And we just assume that the physics is Newtonian, right? Um, and we go, okay, if we have Newtonian physics in a rotating frame, but black holes are actually too large for Newtonian physics, of course, right? They're one of the objects for which general relativity has to take place. So the equations of Newtonian physics are going to be incorrect, right? So let's take Newtonian physics as our starting point, and let's learn correctors to the equations such that we get the more advanced physics that would be the perturbations that are involved with general relativity, right? So you take this and basically say, okay, let's learn how general relativity's equations on binary black hole systems are different from Newtonian physics. And just from a few different data points here, it's able to train and be able to extrapolate forward. Here's in blue is the true waveform, and then in orange is the learned waveform. So you can see just from very, very, very few bits of data, it's able to learn what the perturbation of the equations are, and then it's able to extrapolate fairly well, right? This is something that we've actually turned into tutorials and training materials. So here, let me actually pull this up just so that way I can show you how to get there. If you go to docs.sciml.ai, and go to the automated model discovery, discovering relativistic corrections of binary black hole dynamics, right? This is now one of our textbook examples, right? So you can read through this example to be able to recreate it yourself. But basically, you start from a Newtonian physics, which for a two-body system, right, has an elliptic solution, and then you learn the perturbed solution, which general relativity gives to a two-body system, which is actually this Lysagy pattern. The perihedron of Mercury is the classic example for that was first found, right? And so this is all done just by saying, let's assume we have Newtonian physics. Let's put neural networks into the model. Let's learn what the corrections are, and then boom, it spits out the corrected dynamics, and then you're able to extrapolate fairly well because it's learning, it's learning how the dynamical system has changed, right? This is the view of the two-body system in phase space, and if it's learned how everything works correctly in this phase space, you can keep extrapolating over and over and over in time, but that's just interpolating in phase space. And so like if physically is giving you something that really is meaningful and makes sense, right? And that's really one of the key aspects of these kinds of scientific machine learning methods, right? You're bringing in a lot of information, and what you're learning is very small, and you're also rechanging the way that you're representing the problem. So that way, instead of extrapolation, you're doing interpolation, and you know that that is going to make the machine learning a lot better. Now, this whole topic on universal differential equations and ways to learn models and such, I've given copious other talks specifically about that topic. So I just say go to YouTube for more information. I want to move on now to the topic of, specifically going into depth on the mathematics of how these things are trained. Not, so these other things, if you search on YouTube, you'll find more examples of, this being used in biological systems and in pharmacology and yada, 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 right? So more examples of this working out in practice. That's a separate talk. I want to go into detail on how do you actually do the mathematics behind training these kinds of objects where you have equations and you have neural networks all mixed together, right? So how are these neural networks trained? So the case that I want to highlight here is something that we did on climate models, right? So this is the ocean parameterization problem where you take a column of ocean and you say, okay, what I want to do is I want to change this column of ocean, which is a three-dimensional partial differential equation. It's the Boston-Ness approximated Navier-Stokes equation, and I want to find a one-dimensional PDE that gives me the flow of heat going up and down. I don't want the three-dimensional behavior, right? Now, this is actually kind of difficult to do. It might because the Navier-Stokes equation has curl, and curl is not even defined in one dimension, right? And so actually finding a one-dimensional approximating PDE is actually impossible. But what we want to do is we want to find a one-dimensional PDE that is the average heat flow that is as close as possible to the real 3D dynamics. And the reason why this is done is because when you build a climate model, right, most of the world is the ocean, and so you're going to have a lot of blocks of ocean, and you want to basically not have to run a three-dimensional Navier-Stokes model over the entire Earth. You want to have a lot of one-dimensional models that you then couple together that are high enough fidelity, right? So this is where the ocean parameterization problem comes from. We had an early preprint. We also had an updated one that went up as well, right? And so how is this actually done? Well, this ends up being a perfect case for these universal differential equation types of approaches because you can basically say it's almost diffusion advection problems plus a perturbation, right? And this is called the convective adjustment equation that you see inside of the every climate model. But what we're saying is that we're like, okay, the standard climate model's convective adjustment is close, but it's not necessarily correct. And the way that we could correct this is we can add there's a whole Taylor series of extra terms that are lopped off in the derivation for this statement that, oh, the three-dimensional Navier-Stokes moving heat up and down, the first order of the Taylor series is this term right here. The next order of the terms is everything else, right? And so normally you just chop it off and just say, yeah, the approximation for how the average heat goes up and down is diffusion. But that's not actually true because, again, you have to approximate the one-dimensional approximation of curl. And so there's some aspect that's lopped off, right? So this is called the closure problem. Now,
So Chris, sorry to
yeah.
interrupt, but I had a question. So how did
Oh,
you
please
actually
interrupt. Yeah.
generate the training data for the T? I'm assuming each block is three-dimensional. So did you take an average with respect to height for
Yeah.
the?
So that's what I'm going to describe now, right? So,
Okay.
okay, here's a one-dimensional PDE, and we want this to give us the dynamics of how heat on average flows up and down here, right? So, how should we generate our data is the real question here, right? So, one thing that you can do is you can say, hey, look, I'm trying to train a neural network that is correcting the derivative, right? So what I could do is I can build an approximation to this operator, right? Like a finite difference stencil, build a correction to this operator, finite difference stencil. And what I can do is I can solve a three-dimensional Navier-Stokes, build a data set of exactly this type of animation, and then I can get derivatives of the average of heat flowing up and down in each spot, right? And I can then correct those with respect to the inversion of these operators, and then I basically learn, here's the derivative that I see in my data, and here is the derivative that I should get, and that difference is what the residual that the neural network should be, right? So I can build a whole data set of all these residuals. I can train the neural network, give me something that matches these residuals quite well. Okay, and that's what I'm showing here. You can build a loss function that's directly on the neural network. And the nice thing about this approach is, there's no machinery that's required. You can go to PyTorch and just say, here's my data set of, inputs to the neural network, which is, the inputs to the neural network, which is the current, location and the current temperature. And then the output is just the residual of the difference in the derivative from the data set. And that's the thing that we want to match, right? And so you can just say, okay, let's make the neural network match the derivative. And then after we've trained the neural network, we can stick it into the simulation, right? And if you do that, what you notice is actually you notice that this training problem doesn't actually work out very well. And it actually has a very specific behavior, which is that over time, the error with respect to what your model will give you with the neural network plugged in there versus the original model will actually it will strictly grow in error, right? And that's a very specific behavior because if you think about this from a controls perspective, this is exactly what you would see if you had a derivative control, right? So if you can almost think about this as I wanted to correct the derivative to be correct. And so I put a control on the derivative, this neural network. I'm controlling the derivative to be correct. And I get this drift that's going on, which is exactly the issue if you ask a controls engineer to only correct derivatives in their live machinery, right? So if you ask a controls engineer, how would you correct for this drift that's going on in your training process? What they would tell you is, this is why we have, PID controllers where derivative control is only one aspect. You always need to control the integral. If you don't control that the integral is correct, right? If you only control the derivative, you never really come back to the correct point, right? You always have this growth in your error. But if you control the integral, then you can know that, hey, right here, there's this difference, and I always need to be getting that difference back down to zero, right? That effect is not going on if you train the neural network in isolation. Another thing to mention here is that, if you train the neural network on data and then you put it into your simulator, all the errors of your simulation process, which there will be, right? There's truncation errors and such. None of those are taken into account in the fact that this residual shouldn't actually just be the residual against your data. It's a residual against your data plus some, the artifacts of how you will solve this PDE differently than you will have solved the three-dimensional PDE, right? So all of these pieces together tell us that training a neural network in isolation to match the derivative and then sticking it into the simulator has some numerical issues that will not that will then be compounded, and this gives you something that you can actually see in the results, right? What you can do instead is you can say, okay, let me train this where let me just train this by solving the differential equation, solving the partial differential equation with the neural network inside of there. This will give me a whole average temperature profile. And instead of looking at the derivative data, I'm going to look at the data for what is the average temperature at every single point, right? What is the average temperature going up and down this model? And I'm just going to compare the solution to the PDE with the neural network in there versus the solution versus the temperature data, right? So again, this is looking at the temperature data itself instead of the derivative, the residual and the derivative of the temperature data, right? And the difference between the two is actually quite phenomenal. The second one gets you about like 2 to 3 orders of magnitude better predictions in terms of with the same amount of data, you're able to train using this form to give you a neural network where the predicted equations are about 2 to 3 orders of magnitude more accurate. In fact, if you look at the same plot over here, you'll see that the neural DE in this form is actually pretty much line over line over the before we saw that they were kind of off from each other. There's this drift issue. But now I just say, hey, look, I'm training it this other way. And now they're virtually indistinguishable by eye. So we put this other plot over here to show you that, yeah, there's a difference. It's around 10 to the minus fourth of a difference now, right? And again, it's the same exact data. Right, same exact number of runs for that we're training on. The only difference is that instead of training to get the neural network and then put it in the simulator, what we're doing is we're saying, let's actually train with the simulation process, right? Our loss function is solve with the neural network inside of the simulator, and then check the error of the output of the simulation versus the data, right? And that gives you this major difference because there's 2 ways to interpret it. One is that you're controlling the integral to be correct. So it's a self-correcting process, right? For the same way that a PID is, right? But the other aspect of this is that it's actually taking into account all of the numerical issues of your simulator inside of the loss function, right? It's actually training the neural network to account for the fact that your simulator will introduce its own errors. Those errors and biases are inside of this TNN, and so it's being captured within your loss. And so your neural network's actually being perturbed to account for those pieces of information. Either way you want to think about it, both of those end up being true. But this leads us to the core point, which is that how do you do the scientific machine learning well? You define loss functions where you actually have to have the simulator or the solver for your equations inside of the loss function, right? Like training your neural network separately and then putting in your loss function is possible, right? And the main way a lot of people in some SciML places and like climate science and stuff, that is how they're doing it, right? You train a neural network to match a piece, and then you stick that neural network inside of your final simulation, and you see, wow, that does do some good things, right? But the point is that you can get orders of magnitude more accuracy if that neural network is trained to account for all the subtleties of your simulation process by training it in tandem with the simulation process rather than separately, right? And so you go, okay, cool. Like that's fantastic. That's all you have to do, and then suddenly everything goes well. What's the issue here? Well, the issue is that now that we have the simulation process as part of our loss function, right? If you want to say do gradient descent, then the derivative of our loss function by the chain rule includes the derivative of our simulator with respect to the parameters. And it turns out that one small change gives us this entire mathematical discussion, which is how do you compute that derivative well, and is that derivative actually well behaved? So then this brings us to an intermediate summary here, right? Scientific machine learning, right? We can just say it's scientific models plus machine learning, right? And doing scientific machine learning is differentiable scientific models where we train the neural networks, right? So we have to we stick simulation processes together with neural networks and we train those, right? Now, how are we actually going to differentiate the scientific models? Well, the key idea that you'll go to is, oh, if I just define this loss function in something like PyTorch or Julia, I will just call automatic differentiation and it'll give me the derivative. Done. That's all we need, right? So differentiating, so doing scientific machine learning is sticking the scientific models with machine learning. Doing the SciML is differentiating those scientific models to do the training. Differentiating the scientific models is automatic differentiation. Automatic differentiation is floating point accurate. And so therefore all of this is simple, done, boof. We've now solved the entire problem, stick neural networks everywhere, right? What could be wrong about that statement? Just to be able to be able to show that this can go wrong, I'm going to use some of the Python tools which don't have corrections to the derivatives. So using standard automatic differentiation algorithms where I can show you exactly what goes on using equations that have analytical solutions, right? So here, for example, I'm pulling up diffrax, right? Diffrax is a Jax-based ODE solver that is made for machine learning, right? So it's kind of this lineage of machine learning tools rather than like the classical numerical analysis, type of field. And so it takes a lot of these shortcuts of a lot of machine learning tools, right? So let's actually see what happens when we take one of these tools, right? What I'm doing is I'm defining a very simple, non-stiff, simple linear ODE, right? This linear ODE is just as follows: x prime equals a times x minus y, and b prime or y prime equals b times y minus x. And a and b are just one, right? So it's just a linear ODE: x minus y minus x. So since it's a linear ODE, we can actually write down the analytical solution. We can also take the derivative of the analytical solution with respect to A and B, because this is all the analytical solution, just, initial condition times the matrix exponential of AT, right? So we can actually write down and know the entire everything about the solution, right? And so this is your undergraduate ODE class can write down what the analytical solution of U of t is, and it can also differentiate, du of t dA, du of t dB, because you can use this analytical solution, right? So this is a nice test case to then check what happens if we calculate the derivative using automatic differentiation, right? We know we can calculate the answer. Let's see what their tools tell us, right? And our tools actually tell us that, if we use finite differences, right? So let's calculate the derivative. Let's calculate the derivative with respect to the initial condition, right? So we'll just differentiate with respect to the initial condition, where the initial condition is 1, 1, right? And so we perturb the initial condition a little bit, right? We do this, and here's our finite difference method, right? And tells us that the derivative is about 11,013, right? And analytically, our derivative is 11,013. So this is actually a very numerically stable function. Finite differencing gives us seven different digits of accuracy. But you want more digits of accuracy, and automatic differentiation is floating point accurate, right? So let's use automatic differentiation instead. And you call automatic differentiation, the standard Jax automatic differentiation call in this function. It tells you the answer is 3,755. That's about 60% off. You change your tolerance around, and it actually gives you the exact same number as when you change your tolerances. I'll show you why that's odd in a second here, right? That this tolerance actually should be affecting your gradient accuracy. But then you also ask it to do forward mode automatic differentiation. You tell it to use different ways of calculating the derivative in Jax, and they're all giving you 3,755. It's giving you this number. Why is this number popping up? Like, we know analytically that it's 11,013. This is a very simple linear ODE, but it's 60% off, right? In fact, the fact that it's 60% off shouldn't even be the point. You can construct this example so that way it's as large of an error as you want. The error that this method is giving you in the derivative is actually completely unbounded. Because the point is that it's actually not converging to the correct answer, right? So that should feel odd, right? Like, you call automatic differentiation and it's not giving you the same answer as finite differencing. In fact, it has converged to some constant, and this constant independent of tolerance, and this is actually the wrong constant. And in fact, you can define all sorts of ODEs where keep on going to different constants, which again, it's not necessarily converging to the correct answer. So the point that I'm trying to show here is that numerically, the method that is being used here is actually not convergent. Its derivative is independent of the tolerance. As you send the tolerance to zero, the derivative does not actually converge to the correct answer. So what's going on? Right? For sanity check, we use Julia, and if so you take the same ODE, right? It's just x minus y, y minus x. Parameters are 1, 1. You put this in a cost function, you differentiate it, and forward mode, reverse mode are all 1013, right? With 10 digits of accuracy or whatnot. So what's going on? In fact, you'll notice here is that what should give you a way, something that's a detail here is that when I change the tolerance of the ODE solver, I actually get slightly different derivatives. And so it's actually affecting the solution. The tolerance of the ODE solver is now affecting the accuracy of the gradient of the solution, right? So what is actually going on here is basically what I want to show you is that in Julia, the way that we made this work is that we actually broke the rules of automatic differentiation. In order to make this work, you actually have to make sure that you're not doing automatic differentiation correctly, because the correct definition of automatic differentiation will not actually give you the correct derivative in this point, which that sounds funky, right? So okay, that's a rough claim, right? That automatic differentiation, if implemented correctly, will give you the wrong answer, right? So let me actually show you how this works, right? Because that's a very tall claim. So I need to explain this from the start. So the way I'm going to do this explanation is I'm going to use the dual number algebra version of automatic differentiation. So forward mode automatic differentiation, you can show something very similar on reverse mode automatic differentiation in almost the same way. But what I want to show you, I want to run through how this works and the intuition to be able to construct such examples and why this is failing using a quick explanation of forward mode automatic differentiation, right? So how does forward mode automatic differentiation with dual valued algebras work? Right. So every implementation of forward mode automatic differentiation, whether it's PyTorch, whether it's Julia, whether it's Jax, they're all using something at least equivalent to this. They might use tuples instead of representing the dual, but it's the same thing, right? So the way that this works is as follows. You define a dual number, d equals x plus y, where epsilon is a dimensional signifier. Think about it like it's like I in complex numbers, right? So it's a two-dimensional number. Epsilon's not a very small value. It's a dimensional signifier like I. So we now have two-dimensional numbers. They're given by, two 64-bit floating point numbers. And the rules on this, we define algebraic rules. The rules on this is that f of a dual number is f of x plus y prime plus y times f prime of x epsilon, right? So this is just our rule. The way that you take a function f that's defined on a real number and you extend it to dual number algebras is this rule. And then you also use the rule that epsilon squared is equal to 0. Right. The reason for this rule is that you actually have a nice lemma, which is that if you ever have the dual number x plus 1 epsilon, then what you get out of your function is a dual number that has both the original f evaluated and f prime of x evaluated, right? And so for example, just to kind of show you how it works, like this is an implementation of it in Julia. In fact, you can do a 5-minute implementation of forward automatic differentiation in Julia, just using you build a struct dual of t, which has the value part and the derivative part, right? This is the x and y, and then you just define this on a bunch of functions, right? So exponential of a dual number is a dual number that you do. Well, what's the definition? So you do the exponential of the x part, right? And then you do the exponential, or you do the derivative of your original f, which is, again, the exponential function. And you apply that to your x part, and then you multiply it by this y part, right? So f dot dir. So this is the definition, right? And inside of the course notes for the class, which you can go to book.sciml.ai. If you go to the 8th lecture, this goes into copious amounts of detail on how forward mode automatic differentiation works, how it's derived, and it actually builds a forward mode automatic differentiation engine as part of the notes. So if you're curious about this in more detail, I would say check out book.sciml.ai, look at the 8th lecture. But the point is that this is how forward mode automatic differentiation works, right? You basically just evaluate your program using dual numbers, And then when you want to calculate the derivative, what you do is you construct the dual number x plus 1 epsilon, and you stick that into your function. And then what your code will do naturally is it will give you a two-dimensional output where the first part of that output is the original solution of your function, and the second part of that output is the derivative of your function with respect to the input, right? And it sounds like it's magic, but the way that this actually works is just that this right here is actually, this definition is encoding the chain rule into this value, right? So if you think about this as the value and the derivative, right? This is just pushing forward the derivative by the chain rule, and it's pushing it forward at every single point of your code. And so when you get to the very end, it's just it just works out that the composition of all your functions is that now computed the chain rule in this point, right? Um, so that's a very quick introduction to automatic differentiation. But if again, go to these course notes if that's too quick. But the key point here is that you can use this reasoning using dual number algebras to then be able to understand what is the code that is actually being generated by automatic differentiation and what are its numerical properties. You can then find out just by doing the dual algebra, right? So this gives us a tool to be able to look at what automatic differentiation is doing. Let's now apply this to an ODE solver. So take an ODE, right? So u prime equals f of u, writing down like the simplest ODE, right? Let's differentiate Euler's method using automatic differentiation, right? So here's the forward Euler method using just written out, un plus 1 equals un plus h of f of un, right? Now let's say that instead of having real valued numbers, we had un is equal to x sub n plus y sub n epsilon. So instead of using normal numbers, we're now using dual numbers, right? What we do is we plug this into our equation, right? You plug it in, you do the algebra. I have a talk on YouTube which is a 3-hour workshop on what can go wrong with SciML, which it actually, on the whiteboard, I do every step here, right? But if you plug this in and then you use the rule here that f of a dual number does this, yada, yada, you expand out this whole equation and then you match terms, right? So you match, oh, here are the terms with epsilon, here are the terms without epsilon, right? You end up getting two equations, right? Again, this is the same kind of thing that you do with complex numbers, right? You'd be like, oh, these are all the terms with I, these are all the terms that aren't with I, right? So you've probably done this in your complex analysis course. Now you're just doing this with an epsilon, and with this as your rule instead of I squared is equal to -1, right? This is now your special rule that you involve. Epsilon squared is equal to 0, and here's our function of value, right? So once you do all that, once you plug it in, you move things around, you find that there's one equation without epsilon, there's one equation with epsilon, which is xn plus 1 equals xn plus hf of xn, yn plus 1 equals yn plus hyn f prime of xn, right? These are your two equations that you get, which if you notice, like the way that automatic differentiation should be working is that it should be giving you a way that evaluates your function so that way it's doing the original thing that your function did called the primal, and then also is doing something that is pushing forward the chain rule, right? And you can see here that in the x portion, it is exactly the Euler's method of your function now just on the x portion, right? There's something funky going on in the dual part, right? So whatever is going on in the dual part, if you then made y0 is equal to 1, that this dual part should be the derivative of your ODE solution with respect to your parameters or your initial condition, right? That's the definition of what that's from the definitions of dual numbers, right? And it turns out that there's another way of analyzing it to see that that's exactly what automatic differentiation is doing, right? So if you instead said, okay, I'm going to do this at the continuous level, right? I have u prime equals f of u. If I take the derivative ddp of both sides, right? ddp of du dt, ddp of f, you do the chain rule, you push the chain rule going forward, you get this equation, which is the classic forward sensitivity equation. And if you then write this down, the way that you would using the classic forward sensitivity equation, calculate the derivative of the ODE solution with respect to parameters, is you would solve this set of ODEs, right? You'd solve at u prime equals f of u, and you would solve this equation at the same time, which is s prime is equal to f prime of u s, where s is equal to du dp, right? So if you just plug in s right here, you'll see that this right here is this equation written up here, right? So why do you need to solve these simultaneously? Well, because in order to know what u is, right, because u is a function of time, you actually need to solve the ODE to know what u is simultaneously to the way that you calculate its derivatives, right? So classically, how you would calculate the forward derivative of an ODE solution is by solving this system of equations. And it should look rather similar because this right here, what automatic differentiation gives you is exactly the same. If you, instead of saying y, if you call that s, you'll notice it's the exact same thing, right? So if you're to apply, if you're to do Euler's method on this and you rename u is equal to x and s is equal to y, you'll see that Euler's method on this system of equations is exactly this approximation right here, right? So this actually shows us what's going on behind the scenes, right? Automatic differentiation is doing a transformation to your equations using this kind of algebra and such, right? Or using other techniques that are equivalent, but it's basically doing a way of saying, hey, look, you have a function f that works on the real numbers, but now I extend it to dual numbers. I extend it to a new space that's calculating both the primal value and the derivative at the same time. And when I do that to Euler's method, I get this approximation, which is Euler's method for these equations, which is actually the way that which is actually the continuous solution for how you calculate du dp. So it looks like automatic differentiation is doing the right thing, right? Like it sends a ODE solver for your original equation to become an ODE solver for this equation, right? Cool. But now the next thing to consider is the numerical properties of that, right? Because if you chose dt to be correct for this equation, is it necessarily true that that same dt is stable for this equation? Right? Now, one of the things that's true about automatic differentiation, again, I mentioned this a little bit in here, but by the laws of automatic differentiation, it's always carrying forward, your primal and your derivative. And by this definition that f of d is equal to f of x plus y f prime of x epsilon, by this definition, by the way automatic differentiation works, you're guaranteed that this f of x, this first part, is actually computed exactly the same as without automatic differentiation is done, right? So but this now what we've done here is we've actually hooked these two together, right? We've suddenly said, oh, the h that I chose to solve this ODE is now, by automatic differentiation, doing this code transformation, is now going to just put this same exact step size into this extra part here. It's going to put that same step size into this ODE. And the question is, are we actually guaranteed that that step size and the way that we're picking that step size is actually numerically stable for this new term? The answer is no, because it's actually a different function, right? And so what the way that you construct this counterexample is exactly to look at the equations where you say, okay, can I find an f such that the extra term for the continuous sensitivity is not as stable for the same dt's, right? And then it's easy to start constructing counterexamples where, yeah, I choose a dt that works. I choose a dt that works for my original equation, but then when it's actually doing automatic differentiation, it's approximating this extended equation, and it's building an ODE solver that's approximating this extended equation using only the time step information, the first one. And so there's the disconnect right there, and it's possible for that process to be non-convergent, right? And so that's what's going on here, and that shows you that, again, automatic differentiation is doing something that's mathematically correct, but it's not necessarily numerically correct because it hasn't taken into account certain things like stability and convergence properties, right? Um, and so you can actually kind of see this, right? So this tells you why the direct adjoint method fails, right? Because this issue with forward mod automatic differentiation on this equation. Why does this adjoint method fail? Well, this adjoint method fails because if you actually look at the paper that describes this adjoint method, they remove a term, right? And their justification for removing the term is it looks like automatic differentiation doesn't have this term. And verify empirically that the model still trained without reduction in performance, right? This term is not necessary for all equations in order to get perfect accuracy, but here's an ODE for which if you don't have that term, you actually do get, reduction in performance. You get a 60% error in your derivative, right? And so, and I think that, it makes the way that they went about it definitely makes sense, right? Oh, if automatic differentiation doesn't need this and automatic differentiation is accurate, then, then we don't need this term in our analytical derivatives, right? But it turns out that this term is there for a reason. And so let me, so to be able to describe this, I want to describe what did we actually do to the Julia libraries to make it robust to this problem. And at the same time, start to describe, then in further detail, what is going on and why you actually have to hack automatic differentiation to be incorrect in order to solve for this problem, right? So how did the Julia libraries fix this? There's two ways to explain this. One way to explain this is that you basically need to make sure that you choose your step size. Like, so if you have an adaptive algorithm, right? Because this should be the thing that's coming to mind, right? Diffrax has an adaptive delta t. So why is it not choosing a delta t that will correct for this behavior, right? Now, the what's going on here is that automatic differentiation will make the first part of your equation always be calculated in exactly the same way, which by definition means that the step sizes that it's choosing are the step sizes for the adaptive algorithm on this equation, right? What you want to do then is you want to basically tell automatic differentiation on the hood, hey, instead of making your adaptivity make this equation correct, make the adaptivity make this equation correct, right? Because if this equation is correct, then and the S term is the actual DUDP term, like the derivative of your solution with respect to parameters, then your tolerance is actually affecting not just your original equation, but also the making sure the gradient is correct to the same tolerance, right? So how do you actually do this with automatic differentiation? So you have to actually go into the adaptivity algorithm and see. So, okay, here's how a time stepping adaptivity works in a nutshell, right? What you do is you propose a time step H to step forward with, and then you approximate the solution using two methods. So if you're using something like, ODE 4.5, it has a fifth order integrator and a fourth order integrator that are both evaluated, right? And so let's say that this is the fifth order one, this is the fourth order one. The difference between those two values is an approximation to the error. The way to think about that is that if you do a Taylor series approximation, the fifth order one will get the first, all the quintic terms correct. The fourth order one will all get all the quartic terms correct. And so the difference between them is actually an approximation of the fifth order of the quintic terms of the Taylor series, right? Which is the next truncation error terms, right? So you divide that by delta t to the fifth power, then you get a very good approximation for what your local truncation error is, because that's all the largest terms, right? And so there you go. Now you have a way to approximate your error. And the point is that if that error is larger than your tolerance, well, then you should reject the step and you should take a smaller time step. And until you actually have your local truncation error estimate less than your tolerance. And boom, if that is true, then you accept the step because now you know that your local truncation error is small is below tolerance. And so if it's below tolerance every step, you're satisfying what the user said to you, right? So okay, how does automatic differentiation come into play at this at all, right? Well, if you look at what automatic differentiation is going to do, it's going to calculate both of the solutions with dual numbers, right? So it's going to put forward and it's going to calculate both of the solutions with dual numbers. But when it then approximates the error, right? When it approximates the error, what you need to do is you need to then look at what is the dual number definition of the norm function, right? And what you'll see is that the dual number definition of the norm function inside of the automatic differentiation libraries is to compute the norm of your real part, and the derivative of the norm ends up being effectively zero, right? The reason why that's done is because you need to have in order to do Boolean approximations, like norm is less than one, you need to bring it back to a real number. So what they do is they just say, hey, our norm gives us out a real number by computing the norm of the primal part, and we drop the dual part. And if you do that, if that is your error approximation, then automatic differentiation will calculate the dual numbers for the step of the solution for both of these solutions, and the norm that it will choose for the error will be use the norm of only the primal parts, not the dual parts. And so you'll get exactly the same error calculation as without automatic differentiation. And this will give you exactly the same time stepping as what you would have without automatic differentiation. It's kind of clever, actually, right? So then this makes it so that way automatic differentiation will give you exactly the same step sizes as without it, right? But again, the point is that, oh, we don't want, that's how automatic differentiation will work naturally, and that will give us something that's unstable in certain contexts. So what you can do is you can redefine right here in this spot right here, you redefine that for the error norm, what we do is we make the norm of this error be the norm of the primal part plus the norm of the dual part. Right, so we actually go into the automatic differentiation library and say, my new norm has this as its definition, that I will use this dual part and I will understand that this is now breaking the rules, right? Like this is, if I do that, I am no longer, this definition right here for my norm is no longer satisfying the rules of automatic differentiation, right? But what motivates that reasoning? Well, the reason is exactly comes from here, right? Which is that what we're actually doing when we put dual numbers into the ODE solver is we're solving with a primal part and a dual part. And if we want this to time step exactly the same way as this equation over here, you can actually look at what happens if I did this system of ODEs inside of my ODE solver. The error norm that you would have would be the error norm of U plus the error norm of S. And so if we redefine our error norm to be the error norm of the primal plus the error norm of the dual, then automatic differentiation of our ODE solver will give us the exact same time stepping as if you were have to have written out this system of equations and called the ODE solver on this system of equations instead, right? And that's how we do this connection, right? So we're no longer actually satisfying the rules of automatic differentiation. We are specifically saying, hey, right here in the ODE solver, do not do automatic differentiation correctly, break this rule, and instead use this definition. And if we do that, now it's time-step adaptivity will have this property that when you call automatic differentiation on the ODE solver, it will take different steps. The size of these steps will be completely different, right? Which is maybe a weird property. In fact, it might even take more steps. It might need to take more steps in the context of automatic differentiation. But the reason why it's doing this is because it's now correcting for the error in the gradient, and your gradient will then be accurate with respect to the tolerance, right? And so this then explains a lot of the differences in here, right? Which is that, if you then look at what's changing the tolerance of this ODE solver, it's for this ODE, the Jax method that was chosen ends up having it so that way the accuracy of the ODE solver is actually completely disconnected from the accuracy of the gradient. And so changing the ODE solver around is always going to be converging to this incorrect answer because it doesn't have a term that's actually forcing the adaptivity to go to that. Its time stepping adaptivity is so large that it's actually in the unstable regime, and there's no way to basically tell it through the adaptivity parameters that it needs to get smaller to become stable, right? Whereas what's going on here and within the Julia codes is that because it has basically hacked automatic differentiation to take into account the gradient as part of its time-stepping adaptivity, when you change the tolerance around, you also get a different gradient because that is actually part of this time-stepping. Now, the interesting differences between these is that if in the Jax code, you will if you run your ODE solver with one set of inputs, if you then use automatic differentiation, you're guaranteed that it'll use the same steps. Whereas in the code over here, by definition, by this solve call inside of this cost function during automatic differentiation will take a different number of steps than if you were to do it outside of the loss function, right? So there's kind of an engineering trade-off that is being made here. But this shows you, exactly why this trade-off is being done. It's because this is actually a property that's required to get convergence, which is probably something they might not have thought of before, right? Again, I think a lot of people walk into the space saying, automatic differentiation is floating point accurate, so I can just use it, right? But this shows you that when the problem with the numerical analysis is that it's basically a study that mathematically correct statements do not necessarily give you numerically correct statements when you implement them on a computer. And it turns out that really comes into play in the differentiation of scientific codes. There's a lot to say about the adjoint method as well. I want to kind of quickly go through this. Yeah, so if we decrease the tolerance in the Jax code, does it fix the grading commutation? That's a question that came up in chat. No, it does not, right? Because the default tolerance here, right, is 1e minus 6. And I show you 1e minus 6 and 1e minus 3 gives you exactly the same. If you put it at 1e minus 12, it gives you exactly the same as before, right? And the reason why you know it's exactly the same is the proof of what I mentioned on the other side there is that the time stepping actually does not change at all. It's actually the time stepping is completely disconnected from this tolerance with respect to this gradient. And so every single value of the tolerance, even if you make it 1e minus 20, you'll still get exactly the same value, right? Yeah, so you can move it around all you want. It's basically because of this property, the tolerance does not actually do anything about that gradient accuracy. You have to change your error norm in order to have a connection between that gradient accuracy and the time stepping algorithm to actually then be able to allow it to be able to make smaller time steps to be able to fix this problem. Which again, there's nothing implemented wrong about Jax. It's implemented completely correctly. It's just that the mathematically correct implementation of automatic differentiation on this ODE, again, it's a simple non-stiff linear ODE, but on this ODE, it gives you something that is not convergent to the correct answer. And these are the kinds of things, in numerical analysis you really look into, right? It's this like, just if I wrote down something mathematically correct, do I always have convergence, right? And this is when you go into the mathematics of this, you do find that yeah, the way that automatic differentiation works does not guarantee convergence without this change. And there's a lot of ODEs for which it will work, right? There's a lot of ODEs for which it will be okay. The point is that the error is strictly unbounded, right? You can always define different ODEs that will give you any level of error in this gradient that you want because of this property of how automatic differentiation works. So it's strictly not something that you can prove is convergent in general because there's counterexamples for which it does not converge, right? Um, but again, that's true for the Julia automatic differentiation implementation as well. The only reason why the Julia ODE solvers don't have this property is because we specifically tell automatic differentiation to do the wrong thing, right? And that's like a requirement to get this convergence property. So it's a nice little example to show you that you really have to think closely about how you calculate derivatives, right? And this is also true with the adjoint method. I want to kind of really quickly mention this case as well, right? Because the PyTorch library is kind of they went through and said, okay, with the neural ordinary differential equations paper, here's the adjoint method, right? You solve an ODE going forwards, and then you solve an ODE going backwards, specifically this ODE, and this is a way to calculate the derivative, right? And so you can once again ask the question, right? Okay, there's nothing wrong with the math here, right? The math is completely correct that if you solve this ODE going forward, or you solve this ODE going in reverse, ta-da, you'll get the derivative, right? The question is not whether the math is correct. The question is the implementation of that math guaranteed to give you stable and accurate convergence solutions, right? And that's this difference in numerical analysis, right? It's like, when you learn about the Euler method and you go, okay, you actually have to have H sufficiently small to get the right answer. And on hard equations, you need to use implicit Euler, right? This kind of convergence and stability things that you have to look at in partial differential equations. How does that apply to the adjoint method, right? Specifically this adjoint method, which assumes you can do reversing. Um, which, again, you can go to the Jax library and you'll see that this version of the adjoint actually has this property that if you change the tolerances around, it'll change the gradient. So the backsolve adjoint is actually something that will correctly converge on this ODE. Because this version, the analytical derivative, actually is doing error control on the time stepping with respect to that error in this term right here, right? So it's actually this version of the adjoint, the backsolve adjoint, will actually converge to the correct answer there, right? But why is this then the adjoint that's not recommended in the documentation? Well, the reason is because it's relying on a numerical property that's not always true, right? So we're saying solve an ODE going forwards, and now because u prime equals minus f, solve this ODE in reverse, right? It turns out that this statement right here is mathematically correct, that you can solve the ODE and go in reverse, but it's not necessarily something that's numerically correct. And one nice way to be able to show that is on the advection equation, right? So in the advection equation, right, you have du dt is equal to du dt plus a du dx is equal to 0, right? You probably learned in your linear PDEs course that there's two ways to be able to handle this du dx term, right? You can either do the forward derivative, right? So you can either say use the x value from in front of you or the x value from behind you, right? This is upwinding and downwinding, right? And in your linear PDs course, you probably did a von Neumann analysis to be able to show that if you choose the wrong winding, right? If you choose the downwinding method, that one of these gives you unconditional instability for the solution, right? There's a nice way to be able to prove this just by eye though, which is that this ODE right here. Right, so the analytical solution to the advection equation is the wave is moving to the right, which means the analytical solution to what value you have to be next is the value to the left of you. And this ODE right here only has the current value and the value to the right of you. So the value to the left of you, which again is the analytical solution for what your value should be in the next step, doesn't even show up in the update equation. And so it should be immediately tell you that there's no way that this way of writing down the ODE is ever going to give you the correct answer, right? Because with the value that is actually the analytical solution doesn't even show up in the update equation, right? And so again, von Neumann analysis is really the way that you prove the stability of the upwinding system, right? But really from this, like, okay, I have to do upwinding. If I choose the wrong ODE definition, then I have unconditional instability, and my solution goes to infinitely fast, right? And so we all know this as like this is the standard linear PDEs of introduction to hyperbolic equations and 1D conservation laws. Why does this matter? Well, it matters because we're now let's think about what happens if you apply this adjoint method to this type of equation, right? You solve the ODE going forwards, it's doing upwinding. You solve the ODE in reverse. When you reverse the ODE, the wave's going in the other direction. So if you did upwinding, if you did downwinding in the forward direction, you already got your solutions numerically unstable, right? But if you did upwinding with this, and then you call the adjoint method, then you're now actually downwinding when you do the adjoint calculation. Which, if you actually do this, if you just type this into the PyTorch ODE solver, and then you ask its derivative with respect to many steps, it'll tell you that the gradient's actually equal to infinity. Why is the gradient equal to infinity? Well, because it's using downwinding on the reversed. When you reverse the ODE, inside of that adjoint method, it's doing downwinding, and that is not a numerically stable calculation for how to do this u prime equals minus f. You actually have to redefine f to be this other ODE in order to make sure that it's going to be numerically stable, right? And the adjoint method doesn't know that. It just uses the same f inside of the equations, right? And so boom, then you end up with this instability, right? So if you go to torchdiffeq, you can then just write out the discretization of the edge of the advection equation with upwinding, and you'll see that when you ask it for this gradient, you get this infinity. And this is why, right? This is a fundamental problem then with this implementation of the adjoint, right? And there's a paper that we have that goes into this in a bit more detail. It's called Stiff Neural Ordinary Differential Equations. It turns out that this is a property that you can look at just the Lipschitz constant of the ODE. And as the Lipschitz constant of that ODE goes to say, minus 50, so you have an ODE which is converging to 0, which is the linear ODE, right? It turns out that when you reverse that ODE, you have this exponential growth in reverse. And that exponential growth in reverse is actually causing exponential growth in the error. And so just having a lambda of minus 50 makes that adjoint method have an error of 10 to the 12th, right? And so you can see why really quickly for any stiff ODE, which is where lambdas are going to be large. For the advection equation, this adjoint method will fail, but also for any stiff ODE, you also get great infinites in your gradient. And this just comes from this property of the irreversibility of many ODEs, right? And so this means that when you do the adjoint method in practice, you actually need to be a bit more careful, right? Just because that statement that I can reverse my f is mathematically correct doesn't mean it's necessarily numerically accurate. And so you need to do something like, for example, always only solve u going forwards, and you might need to like store the interpolation, or for example, what Sundial's first came up with is it has a checkpointing approach, right? There's these different approaches that avoid ever making this assumption. And those are required in order to get this numerical stability. And I think that since I think I'm kind of going over time, I think that I'll end there. I'll end on this that we recently had a paper that we put to that we're putting out on differentiable programming, a review. Differential programming for differential equations and review. And this goes into detail on a lot of these issues about so this archive paper right here. This goes into detail with a lot of the derivations and such of some of these counterexamples where different ways of calculating the derivatives can give you different inaccuracies and non-convergence properties and such. And so basically what ends up telling you at the end, let me, because I forgot to put this this chart in here, right? Basically, what ends up telling you is that just like how you have different ODE solvers for different types of equations, it turns out that the way that you calculate the derivative needs to be different depending on the type of equation and the different types of properties, right? Some of them are more stable than others. Some ways of calculating them, like should I incorporate the duals into that error term? The answer is maybe, right? Because that will increase your stability, right? But it will also make you take more time steps, right? So which one is correct for your equation? Well, if the way without it is sufficiently accurate for your equation, maybe you don't want to do that. But, if you want to be safe, you can always do that, right? So, there's differences in these methods between how they have stability They have performance trade-offs and also memory trade-offs, right? So the reason given inside of the neural ordinary differential equations paper for this way of computing the adjoint is that it's O of one in memory, right? And so this is exactly that backsolve method, right? Which is that it has very bad stability, right? It assumes reversibility, so ends up being more unstable than most other methods, but it has the best memory usage of any of them. It's O of one in memory. Um, so again, so really just like how you have, non-stiff ODE solvers and stiff ODE solvers, the point is the way that you calculate these derivatives can be very different and they give you very different properties in ways that you might not have expected at first. And so the real core of doing scientific machine learning correctly and writing these libraries and the behind the scenes of it is the numerical analysis of how you calculate these derivatives is as deep of a subject as the ODE solvers themselves. And it turns out that there's many trade-offs to be made here. And whether a library is doing the right trade-off or not is kind of dependent on the use case, right? So what we do, again, the Julia scientific machine learning libraries, we make a lot of these versions such that we just assume that we want to have convergence on as many equations as possible. And so we include each of these things to make sure that we have these convergence. But the downside is that we will take more time steps on some equations because of this extra error term, right? And so, is that the right default or not? We can argue we can argue forever on what the right defaults are. But I think that the point at the end is there isn't just one way to calculate the derivative, and you really need to make sure that you're doing this correctly in order to do scientific machine learning correctly. So thank you. Hopefully that's counterintuitive and it's not something that you thought of before, and hope you find that cool and interesting.
We certainly did, Chris. Thanks. This is fantastic. And actually, I have a question on this,
Yeah, yeah.
and I'll let it open it up to the audience soon as well. So we were trying to actually do some closure model calibrations for turbulent flows. It's kind of similar to your ocean
Mhm,
example. But it was like an LES type of situation, but our vector terms were discretized using a Wino type of scheme. So we
mhm,
had this adaptive upwinding, and we ran into this problem. We were using AD, we were not using adjoint.
mhm.
That no matter what we tried, we weren't able to get any useful gradient. Basically, is it related to perhaps how the discretization shows up? I don't know. Can
Yeah,
you
yeah.
give
I
us some
mean,
thoughts?
yeah, I haven't looked into the Vino case in too much detail, but I have thought about it a little bit, which is
Mm,
that normally when you kind of do these finite volume types of approaches, in order
mhm,
to make sure that you can guarantee the conservations correctly and not get divergence, you need
mhm,
to kind of do some staggered gridding, right?
mhm, mhm,
Um, and don't take me as my as like, oh, this is a fact, I've proved it kind of thing,
mm,
because I haven't done the whole proof and everything, but I have seen this kind of behavior before, and my guess is that when you do this generated equations, right, what forward mode automatic differentiation is going to give you is going to give you that these extra equations it's doing are on the
mhm,
same grid as your
mhm,
original equations. And
mhm.
actually, to get the finite volume properties on the derivative, you might actually have to stagger the derivative calculation, right? Which the adjoint method and automatic differentiation won't naturally do, right?
Okay,
Um,
okay, okay.
so
So yeah, that adds a lot of complications, right? Because and
yeah,
also
yeah.
it's difficult. So when we do this with Phoenix, which is finite
Mhm.
elements, we don't see. I mean, this is lower order, of course. It was not we know, but with these lower order schemes in finite elements, we're not seeing these instability issues. But
Yeah,
uh,
and so that's exactly so so my statement there it aligns with that fact because
right, right.
what Phoenix is doing differently, right? So automatic differentiation is actually taking your discretized version of your code and it's trying
Mhm,
to generate the way to calculate the derivative, right? So
mhm,
it's taking a discretized ODE solver and trying to give you an ODE solver that will be your code, right? When you do the adjoint method on the ODE, it's taking a semi-discretized PDE,
mhm.
and then you're trying to generate a semi-discretized PDE that will give you a derivative, right?
Sure,
If
sure.
if your problem is that the semi-discretization is wrong, right? Which is that your gradient terms need to be staggered from your from your original terms. You actually need to go all the way to your original PDE definition
Yes.
and modify it there, right? The semi-discretization has already lost that information. And
Mhm.
Phoenix is actually doing that, right? For Phoenix, the way that it does its adjoint method is it takes your symbolic PDE definition and it builds the adjoint PDE and it discretizes that PDE, right? And if
Mhm.
you do it
Mhm.
like that, then you can actually do the grid staggering or whatever is needed for you can analyze that PD and make sure you discretize it in space in a way that is actually stable. So I would
Okay.
actually expect that Phoenix on this type of equation would be able to make this stable, whereas automatic differentiation and the adjoint methods, even the Julia ones, Julia Jax wouldn't matter, right? We'll probably give you a divergent derivative on that type
Mhm.
of PDE. Yeah.
Okay. Okay. Thanks. Yeah, that makes sense. It confirms some of the behavior we've been seeing. So
Yeah.
okay.
It's funny that it's not really highlighted in the literature all that much.
Yeah,
I think that
exactly.
what
Yeah.
happens is that people that try it on these types of equations, they go, I can't train neural networks, so I'm just not going to publish anything about it, right?
Mm-hmm.
Like, and so
Mm-hmm.
it's just kind of like this dark area. But I mean, this is a real phenomena that
Mm-hmm.
that you will get incorrect gradients, and so you will find it in the hard equations that people aren't publishing about and like differentiating we know methods. This is what's going on there. So I'm trying
Mm-hmm.
to bring more light to this issue.
Yeah, we really appreciate it. Thank you so much, Chris. Okay, questions from the audience. We're a little over time, so some people had to leave. Are there any questions, the audience? So I have a question about the example you gave in
Mhm,
Jax for
mhm.
not converging to the right derivative. So is there a way you can implement what you did in Julia in Jax as well? I only ask this because some of our code bases are in Jax, and it would be nice to
Yeah,
know how to do.
I'm not sure. I mean, I think it doesn't directly use dual numbers, but there's probably a way to be able to kind of tell it within the error norm, like, hey, look,
Mm,
use these extra
got
values.
it.
So
Got it.
there might be a way to be able to you'd have to do it in the ODE solver library, right? It's not
Got it.
something that the AD library can account for,
Sure.
right?
Sure.
But yeah, there probably is a way to hack it in there in a similar way.
Okay.
I
Okay.
think that there will definitely be some questions about whether whether you should, right? Because again,
Mm-hmm.
there's a lot of odd engineering trade-offs with this, right? That, for example, like automatic differentiation in any other context is always guaranteed to run exactly the same computations and give you the exact same thing on the
Mm-hmm.
primal.
Mm-hmm.
That will no longer be true. It will take
Correct.
different time steps on the primal, right? And
Mm-hmm.
whether that's the best default behavior for the library or whatnot, that's a library choice for defaults and such, right? So I'm
Okay.
sure that there's a copious amounts of discussion to be had there.
Mm-hmm.
With the Julia libraries, we decided that we just wanted to bake this in by default because some users had opened up issues where they said, yeah, here's this linear ODE where I'm getting the wrong solution. We looked into
Mm-hmm.
it. And we said, oh, this is an interesting phenomenon. Let's make sure that we're always good with this. But definitely, then the next thing that we had some people open issues about was, hey, look, I looked at the array that I get for the solution inside the cost function, and I looked at what happened when I solved it up here, and they're different sizes. What are you doing, right? So
Mm-hmm.
it almost invited its own set of questions, right? And we decided that the way that we generally build our libraries is that convergence and accuracy comes first, and then performance second. And if you want faster performance, here's a knob to turn on more performance, right?
Sure.
So we end
Mm-hmm.
up going with this way because it's like, okay, this is the safer thing, but it has a very non-intuitive, it has some non-intuitiveness to it as well. So
Okay.
yeah, I mean,
Great.
you could probably implement it in Jax, but I'm sure people who work with automatic differentiation, they might give you pushback because that's not,
Makes
again,
sense.
you're breaking the automatic differentiation rule, right? You're breaking the way that automatic differentiation is defined. So should you
Mm-hmm.
ever do that? Yada yada. There's definitely discussions to be had.
Okay. Okay. Great. Okay. Well, this is fantastic, Chris. I think one of our best talks. So, let's all thank Chris again, and he's very responsive, very active in the community. So I'm sure he'll appreciate any follow-up questions or emails from you. Chris, thanks a lot again for your time, and hope to run into you at a conference somewhere, and we can chat about this some more. Right?
Yeah, for
Okay.
sure, for sure.
All right. All right. See you around. Thanks.
See you around.